Hi everyone, I am Shubhadeep Chakraborty. Today I will be presenting a paper uh, Dual Diffusion for Unified Image Generation and Understanding. This paper is a part of the Foundation Models and GenAI course under the supervision of Dr. Mayank Vatsa. This paper is authored by researchers from Carnegie Mellon University, Yale University, and ByteDance. So let's go to the next slide. So let's begin with the motivation behind the work. We are currently experiencing a major shift in generative AI, especially with multimodal models. Diffusion models like Stable Diffusion 3 and Imagen produce extremely high quality images from text prompts. On the other hand, aggressive models, for example, GPT-4, Gemini, and Lava, excel at text generation, reasoning, and tasks such as captioning or answering on images. So the question arises, like, can we combine the strength of both worlds in a unified and bidirectional way, like text to image or text image to text? The goal of the paper is to build a single multimodal model that can understand images and generate text, understand text and generate images, and also allow omnidirectional conditioning, which will reduce architectural complexity and move us to closer to general purpose multimodal intelligence, which is an early step toward AGI. So next, move to the slide number 3, the diffusion gap. However, there is a big challenge. Autoregressive models already have some success in generating images using visual tokens, but diffusion models have a major weakness. They are not naturally compatible with languages. The reason is that diffusion works smoothly on continuous data like images in latent vector space, but text is discrete. It consists of tokens, and until recently, diffusion on discrete token was not effective. Because of this gap, earlier multimodal diffusion models had several limitations. They required autoregressive decoders like GPT-2 to convert latent text back to normal text. They had limited reasoning capabilities. They could not truly perform full image text to text tasks like VQA in an end-to-end diffusion framework. In short, diffusion model lacked a reliable text generation mechanism. Now let's move toward slide number 4, which is proposed method dual diffusion transformer, which is our proposed method dual diffusion transformer D-DiT. To address this, the author proposes the dual diffusion transformer or D-DiT. This is the first model that fully unifies images, image diffusion and text diffusion with a single architecture. The key idea is very elegant. First, create two diffusion branches, for one for image latents and one for text tokens, as you can see in the given image, and let them integrate deeply inside a single transformer. The model support all multimodal tasks, which is text to image, image to text, plus text plus images for text, for example BQA, all through pure diffusion without any autoregressive components. Now let's move toward slide number 5, architecture overview, D-DiT. Let's go deeper into the architecture. D-DiT is built on MMDIT, the multimodal backbone of Stable Diffusion 3. The architecture contains two branches, image branch and text branch. In the image branch, it operates in the VAE latent space, compressed representation of the images. Inside the and it learns continuous diffusion through a velocity prediction network. And inside the text branch, it uses discrete masked diffusion on token embeddings, and it learns to reconstruct clean text by predicting the original token distribution. The remarkable part is that both branches share the same transformer layer using cross attention. This way, at Every layer text tokens attend to image tokens and vice versa, enabling strong multimodal fusion. Additionally, the author add a bidirectional T5 encoder on the text side. This improved language understanding and keep the architecture compatible with Stable Diffusion 3 initialization. Let's move to the slide number 6, which is joint training objective. Dual modality loss. The training objective is one of the most important contribution of this paper. Both modalities are trained together using a joint maximum likelihood framework. One is image loss. Based on continuous flow matching, it predicts the velocity field that reverses the diffusion process. Second is text loss. Based on the discrete mask diffusion, NALBO, which is NALBO formulation, it predicts the clean tokens hidden behind mask tokens. These two losses are combined as a single dual modality loss, which is L dual equals to L image plus mod of text lambda of text into L text. A crucial training constraint is that the conditioning modality is never noised. This means while generating text, image is clean. When generating image, text is clean. This ensures a stable conditioning across modalities. Now go through the slide number 7. Here it is training stages. In the training of D-DiT happens in three stages, each serving a different purpose. First is dual diffusion pre-training. It takes 60k iterations. Dataset is recaption datacomp 1 billion, and its purpose is to teach the model that joint image text diffusion from scratch. In the stage 2, it is continual pre-training, which is 200k iterations. Which is 200k iterations. Here dataset we use is shared GPT 4 BIP and open images with rich captions. Here text length extended to 256 tokens. Optionally, here they have also taken 512 cross 512 high resolution fine tuning. Its purpose is improve multimodal understanding and visual reasoning. On the stage 3, it's come visual instruction tuning, where they have taken 50k iteration. Dataset is lava, text, FQA, and viz. Purpose is enable question answering instruction following in longer text responses. Throughout training, the stable diffusion VE here and T5 encoder remain frozen, which reduces training cost and stabilizes performance. Next, come to the next slide. Inference capabilities. Once trained on D-DiT, it can perform 3 major tasks, which is image to text, T2I. Given a text prompt, the model runs reverse diffusion to generate an images. It uses classifier free guidance for controlling image quality and prompt alignment. And second is image to text generation. Captioning, here the model reconstruct clean text tokens using ancestral sampling. Unlike previous model, no auto regressive decoding is needed. This is true end-to-end diffusion text generation. And on the third, like image to text infilling VQA. This is a highlight of the paper. To answer a question about images, the model keeps the question tokens fixed. The answer tokens start as fully masked tokens. The discrete diffusion process fills in the answer sequence. This gives the model genuine text completion capability. Now go toward slide number 9. Here in the result, you can see the model is evaluated on major visual reasoning benchmark, including VQ2, GQA, viz, OKBQA, POP, and MEME. Here, D-DiT significantly outperforms prior diffusion-based models such as diffusion and versatile diffusion. In some benchmarks like POP and MEME, the 512 cross 512 D-DiT means variant even matching or surprises autoregressive model like show. This demonstrates that diffusion-based multimodal learning can compete with next token prediction models, which is previously thought to be very difficult. Next, come to the next slide, slide 10. Here you can see some results based on text to images. For text to image generation, the author evaluated the 512 cross 512 model on GenAI benchmark. Here the key findings are the model maintains aesthetic quality comparable to Stable Diffusion 3. Prompt following improves slightly after multimodal training, as here you can see, and then the model remains strong at composition counting and color accuracy. The quality samples show high coherence and sharpness still diversity. Next, move towards next slide, conclusion. To conclude this paper, firstly, the first truly unified diffusion-based multimodal transformer. It handles both image generation and text generation using diffusion without relying on autoregressive components. Here, key achievement includes unified architecture from text to image, image to text, and VQA, joint continuous plus discrete diffusion. It provides competitive performance with autoregressive VLMs, and it compatibly with standard or Stable Diffusion 3 foundation models. Some limitation and future works are the author also mentioned limitations such as difficulty with complex multimodal multi-object scenes, then occasional failures on tiny objects, and fixed length text diffusion, which cannot yet generate variable length sequences. Future direction includes dynamic length text diffusion and better complex scene modeling, enhanced multimodal reasoning, and more efficient sampling. So thank you for your attention. This paper is an important step toward general purpose multimodal models powered by diffusion rather than next token prediction. Thank you everyone. Have a nice day.